Hi there, my name is Theodore Psillos,
I'm Jessica Andrew.
and we are both students at the University of Cape Town taking the course Engineering Design ECE, Electrical and Computer Engineering EEE3097S with our convener and lecturer, Dr. Amit Mishra.
So just a little context about our project. It is based on creating an ice buoy to be used in the marginal ice zone in Antarctica, which is used to monitor the environmental conditions around the ice flows and how they form and move within the zone. Antarctica has a critical role in our global climate system, and scientists like to constantly monitor it in order to compare it to other data they gather. The current expeditions are using technology that is very costly and to implement and use in the area, as they often lose it. So the buoys that are being used in this experiment had the requirements of having to survive the harsh environments for a sustained period, where they can use remote sensors to record the data in real time and then transfer this data using the Iridium network that is currently deployed into Antarctica, but transferring over this network is quite costly. So our project was aimed at designing a system that can be on the buoy to compress and encrypt the sensor data in order to allow large packets of data to be transferred cheaply.
Right, so this is just a little overview of the whole system that it's interacting, and obviously, as Jess said, we're looking specifically at the compression and encryption blocks of that system. But some limitations that you have to that need to be considered are that we aren't using the exact IMU that is on the board on the buoy, and so we have limitations in the certain sensors that we did use in the SenseHat-B that WaveShare provided us are different to that of the actual sensors on the IMU. Another limitation is obviously we're in very different weather conditions. As the buoy is normally deployed in Antarctica, and one can imagine being situated in Cape Town, the temperatures have a vast difference of roughly 20 degrees or more. So those are just the two main limitations.
Yeah, and then just a quick overview of the steps we took to develop this project. We started with a paper design which analyzed the compression and encryption algorithms on a theoretical level. And we compared multiple different algorithms on many different factors, such as speed, compression ratio, whether they were lossless or not, and their RAM and battery power usage. Obviously, because the buoy needs very certain requirements, such as it has a very strict battery use, so we couldn't use an algorithm that required a lot of power. Once we had developed a couple of algorithms that we thought could be used, we implemented these in Python and tested them on our Raspberry Pi with data from the Loken 21 papers, which was provided to us, which is from an IMU deployed in the Antarctic region, but from a different area and a different research task. From these experiments, the compression algorithm chosen was the BZIP2, and the encryption algorithm chosen was AES encryption. Once we decided on these encryption and compression algorithms, we moved on to use a SenseHat-B, which was attached to our Pi. We simulated the compression and encryption algorithms on the data provided from the SenseHat-B, which was sent to CSV files. We compared the results of the same algorithms on the data from the Loken 21 papers and from the SenseHat-B, and we found that they provided very similar results, therefore showing that our results of using BZIP2 and AES was correct.
Okay, so I'm just going to say cut it there.
Yeah.
How do I stop recording? There we go.
A few moments later.
So we're back on a different platform after technical difficulties. What I'm going to do now is I'm going to demonstrate the Pi or Raspberry Pi working with the SenseHat, and it will be what I'll share. What my screen will be sharing is the actual command prompt or terminal of the Pi that we SSH'd into. So to just share my screen. Okay, I'm going to cut this out of it. Right. So as you can see here, the file that we...
A few moments later.
As you can see here, the file,
Yeah.
the file over here is called Python SenseHat code. That we ran to pull the data from the SenseHat. We moved the SenseHat around, and you can see after 60 seconds the data was produced, and this is the data file and the CSV file that was produced. Then you can see here just below there is the compress encrypt. This is compressing and encrypting all in one go the CSV file, with the password being set, or the key for the encryption being set to password. And you can see that took quite minimal time because the actual file size was very small. It took less than approximately 50 milliseconds. And now we are decrypting and decompressing the file. The compression technique is a bzip2, and so hence the extension, and putting in the correct key gives us the decompressed file. So as we can see here, the actual demo.csv file original size was 28,430 bytes, and the compressed file size is 9 kilobytes, with the compressed and encrypted being 9 kilobytes also approximately. Then the decompressed file, and the decompressed file is 28 kilobytes over there, which is approximately exactly the same as that of the original file. So now to just test that the contents of the file as well as the file size are both the same, we are simulating the test loss data, which has two comparison techniques, deep and shallow, which can be further sort of read about in our report. So you'll see here that it will return true, meaning that the shallow and deep match were both successful and all content was preserved. Cool. So that's basically just the demo of the project. And that pretty much wraps up our report or demo presentation. And for more details, you can read our full report, which will be attached in the description. Make sure to hit that bell notification, like, subscribe, and leave a comment. All jokes aside, though, our GitHub will also be there, where it will have a lot of the code. You can feel free to test the files. The README should have an in-depth description of what program corresponds to what application, and what you need to do to run it. Feel free to pull the Git repo or clone it, and to let us know your thoughts. But that's all from my side. Jess, if you have any last words.
Yeah. No, we're good. Thanks.
Okay, awesome. Cheers. Okay. I almost left.
Cool. Do you want to quickly compile